Hey everyone, I'm Suhas Jayaram Subramanya from Carnegie Mellon University, and today I'll be presenting our work on building a heterogeneity-aware, goodput-optimized ML cluster scheduler named SIA. This is joint work with my colleagues Daiyaan, Shouxu, Aurick, Zhihao, and Greg. Deep learning training jobs are an important class of workloads in today's data centers. Deep learning training jobs run a user-supplied training script on a dataset using GPU-accelerated compute and produce a trained model on completion. These jobs can consume hundreds to thousands of GPU hours per run and can be parallelized across up to hundreds of GPUs in many ways. Sizable deep learning clusters often share the cluster resources among many users that submit their jobs to a central cluster scheduler. The cluster scheduler allocates GPU resources to jobs with the primary goal of minimizing job runtimes. As GPUs become more efficient and as deep learning scenarios evolve, newer models often demand more compute and newer GPUs are incrementally deployed into deep learning clusters, making the GPU resources more heterogeneous over time. GPU resources can also be heterogeneous in many dimensions. Newer GPUs provide higher throughputs and can also incorporate accelerator engines to speed up tensor and transformer computation. Memory on GPUs can also be heterogeneous, with some GPUs offering higher memory capacity at a lower bandwidth as a trade-off. This means some GPU types can hold more working set in memory than others. Finally, the interconnect between GPUs also influences the efficiency of parallelizing the compute across GPUs. Larger models run better with high bandwidth interconnects, so some models may prefer some GPU types over the others. So what does this mean for users who run their jobs on such heterogeneous clusters? Today, they would have to manually tune the varied combination of resources, counts, topologies, and the training batch size so they get the best job runtimes. However, profiling all possible combinations would be prohibitively expensive in both time and resource cost, as the space of adaptivity choices is too large. So users may only spend some limited time on profiling a few combinations and may end up making a suboptimal choice. As a result, the jobs could run longer and use cluster resources inefficiently. Finally, even if users chose optimally, the optimal choice changes over time as model training progresses, and it may not be possible to satisfy every job's optimal resource requests because of limited cluster resources, leading to worse outcomes for some jobs. Enter SIA. SIA is a goodput-optimized scheduler that supports adaptivity for data parallel DL training jobs on heterogeneous resources. SIA continuously optimizes the number and type of allocated GPUs and the training batch size for each job in the cluster to maximize collective training progress. This improves average job runtimes by 30 to 90% compared to the current state-of-the-art schedulers that address either heterogeneity or job adaptivity, but not both. SIA also uses a novel approach to model job adaptivity on heterogeneous resources while using minimal amounts of profiling. By using GPU types more efficiently, training a deep learning model requires 20 to 55% fewer GPU hours when using SIA compared to the state of the art. Further, SIA's scheduling objective can be formulated as an integer linear program and is efficiently optimized in a few seconds even for 1000 GPU clusters. Let's get into some quick background needed to understand our work. So I've told you that SIA optimizes cluster-wide goodput. So what is goodput? Goodput is training progress per second and is defined as a product of two terms: the throughput of a job, defined as the number of examples processed by the training job in a second, and the statistical efficiency of training, defined as the amount of training progress made per example processed by the training job. Throughput can be expressed as examples per second, and statistical efficiency can be expressed as progress per example. So multiplying the two should give us training progress per second. Since we cannot predict the runtime of a job, SIA uses goodput to guide allocations, since higher goodput means more training progress per second, so jobs should complete quicker. Since goodput is a function of batch size, for each possible allocation, we can optimize over the range of batch sizes to find the maximum goodput possible on the allocation. The plot on the left shows the goodput of a job training Deep Speech 2 model on the CMU Arctic dataset. The x-axis is the number of GPUs and the y-axis is the goodput of the training job at halfway completion point as a function of the number of GPUs. The three curves correspond to three different GPU types, where the green corresponds to the peak goodput on the A100 GPUs. we see that the goodput curves scale similarly for both the A100 and RTX GPU types. So the two types are equivalent for this job. Other models may, however, show a different scaling behavior. Consider this plot in the center. This shows the goodput curves for a job fine-tuning the BERT model on a squad dataset. Running this model on the A100 GPUs gives us significantly more goodput per GPU compared to the RTX and T4 GPU types. So, if you run a mix of these two model types in a cluster with these three GPU types, we would want the BERT jobs to run on the A100 GPU types as much as possible for best efficiency and run the Deep Speech 2 models on the RTX GPUs as we can get equivalent performance as A100s. Finally, since goodput tracks the optimization progress in the training job, batch size with the best goodput changes over time. The plot on the right is borrowed from Pollack's OSDI 2021 and shows the best batch size with the highest goodput on the y-axis and the number of GPUs on the x-axis. The two bars show the first and the second halves of the training, and we see that the best batch size changes over time. As training progresses, the model tends to use a larger batch size, and so a job's goodput curves also change over its lifetime, and its allocated resources must be continuously optimized to minimize its runtime. Let's take a look at the landscape for deep learning cluster schedulers in literature and plot the schedulers on two axes. The y-axis is the resource heterogeneity defined by the scheduler's ability to schedule jobs on heterogeneous resources, and on the x-axis is the job adaptivity determined by the scheduler's ability to optimize resource count and training batch size. On the bottom left, we have schedulers like Gandiva and Themis that do not support either job adaptivity or resource heterogeneity. Optimus and Shockwave both support optimizing some number of GPUs to some extent, but not training batch size, and sit halfway along the job adaptivity axis. Pollack supports full job adaptivity, but only on homogeneous clusters, and falls in the bottom right corner. On the heterogeneity axis, we have schedulers like Gavel and Gandiva Fair that can schedule jobs on heterogeneous resources, but do not take job adaptivity into account. We want to optimize job adaptivity on heterogeneous resources because GPU resources are fungible. For example, for some jobs, our A100 GPU could provide the same goodput as two V100 GPUs, making them fungible. SIA exploits this fungibility of GPU resources to optimize over the combined state space of job and resource adaptivity choices in a heterogeneous cluster. Let's get into the details of SIA and its components. At its heart is the SIA scheduler loop that runs once every 60 seconds. This loop involves mainly three components. First, the scheduler policy, seen on the top left, uses goodput models to guide job allocations. SIA then realizes these job allocations by placing the jobs on the allocated resources and starts executing the jobs, as seen on the bottom right. As the job runs, SIA profiles mini-batch times and gradient statistics and refines its goodput models using the profiles collected on the allocated resources. The refined goodput model is then periodically communicated to the policy, so SIA always uses the latest goodput models to decide job allocations. Let's quickly take a look at each of the three components. SIA policy uses the latest goodput models to guide the allocations by running an optimization program to maximize cluster-wide goodput. In this figure, SIA policy uses the goodput model for the A100 GPUs and decides to allocate two A100s to the job, denoted by the two green symbols up top. SIA then places the job on the two A100 GPUs and uses the goodput estimator to select a batch size that maximizes its goodput on the two GPUs. Once the job starts running, SIA periodically profiles the mini-batch times and the gradient statistics and sends the collected profiles to a goodput estimator. SIA's goodput estimator runs inside the training job and builds one goodput model for each GPU type. It periodically refines the goodput model using the collected profiles and pushes the updated model to the policy. In this figure, the clock symbol denotes the collected profiles on two A100s, and the curves under it represent the current unrefined goodput model for the A100 GPUs. Upon refinement, this produces the refined goodput model for the A100s shown in the green on the left. SIA also uses its goodput estimators inside the training data loaders to determine the best batch size for training given the allocated resources. SIA optimizes over a set of allocations called configurations. Configurations serve two purposes. They reduce the search space of allocations and job adaptivity options and make optimization tractable on the reduced search space. A configuration is similar to a virtual machine instance type and defines the GPU type, count, and topology for an allocation. We can define configuration as a 3-tuple with number of nodes, GPUs, and the GPU type as the entries. Consider a toy cluster with 2 nodes, each containing 4 T4 GPUs and connected by a 25 gigabit link. For this cluster, SIA defines the following configurations within a node. 1 T4 GPU represented as 11 T4 on the right, 2 T4 GPUs represented as 1, 2 T4, and similarly 1 4 T4 representing 4 T4 GPUs. For multi-node configurations, SIA only uses whole nodes, giving us the 2, 8 T4 configuration. Partial multi-node allocations are not allowed. For example, this allocation that spreads 2 GPUs across 2 nodes, or this asymmetric allocation that spreads 3 GPUs across 2 nodes. Using configurations, SIA only needs to optimize over tens of allocation choices even for 1000 GPU clusters. Please refer to a paper for more details on constructing configuration sets for heterogeneous clusters. We compute goodput for each job in every configuration and populate a goodput matrix as shown in this figure. The first value 1 corresponds to goodput of the first job on the first configuration with 1 T4 GPU. Similarly, the third value in the first row would correspond to the goodput for the first job in the third configuration, here 3.55. Then, we simply find the job and configuration pairs that maximize the cluster-wide goodput while ensuring that no GPU is oversubscribed and that each job gets at most one configuration. We formulate our search as an integer linear program, and using off-the-shelf solvers, we can quickly recover the optimal job and configuration pairs that maximize the scheduler objective. For the next round, we allocate the optimal configuration to each job so cluster-wide goodput remains high. SIA uses minimal profiling to populate the goodput matrix. Consider a cluster with 2 GPU types, A100 and T4. Before a job starts running, SIA first profiles its throughputs on one A100 and one T4 GPU on a few batch sizes. Say this job then starts running on T4 GPUs and gets scaled up to 4 GPUs. The goodput model for T4 GPUs would be accurate as it is refined using profiles collected during execution. Without profiles on the A100 GPUs, SIA cannot determine the goodput scaling on the A100s. To get around this problem, SIA bootstraps a throughput model for A100s by multiplying the refined model for T4 GPUs with the ratio of the job's 1 GPU throughputs on A100 to T4 that was obtained during the initial profiling. SIA uses the bootstrap throughput models to guide job allocations, and when the job runs on A100 GPUs, we can discard the bootstrap models in favor of the refined models. We'll briefly go over some of our main results from our paper. This bar chart shows end-to-end results in simulation for a 64 GPU heterogeneous cluster with 3 GPU types. We create synthetic traces from a real-world data center trace and record average and 99th percentile job completion times, make span, and the average GPU hours consumed to complete jobs in the traces. Gavel is inelastic, and we provided an advantage here by tuning job hyperparameters before submission. On this trace, SIA reduces job completion times by 72% while using 60% fewer GPU hours compared to Gavel running tuned jobs. Pollux, however, does not differentiate between GPU types and runs jobs 40% slower than SIA using 35% more GPU hours. In our extensive evaluations using 2 more real-world traces, we find SIA reduces average job completion times by 30 to 93% and uses 12 to 55% fewer GPU hours to do so, and presents a new state-of-the-art to optimizing job adaptivity on heterogeneous resources. SIA also uses GPU types efficiently. In this figure, we plot the average number of GPU hours required to train each job to target accuracy, normalizing each model to the most efficient scheduler for that model. Stacked bars correspond to schedulers with P for Pollux, S for SIA, and G for Gavel, and colors correspond to different GPU types. Let us look at 2 familiar model types, Deep Speech 2 and BERT. Here are the goodput curves for reference. Since BERT provides significantly more goodput on the A100s, SIA places it almost exclusively on the A100s for efficient execution. Deep Speech 2 does not favor A100s as strictly, and it receives more time on the T4 and the RTX GPU types, reflecting the job GPU type preferences we see in the goodput curves. SIA also adapts jobs allocations to cluster conditions. This graphic shows CR allocations for a few jobs running in a 44 GPU heterogeneous physical cluster with 3 GPU types. Here, colors indicate GPU types, and the height of the shaded area shows the number of allocated GPUs. And the bottom plot shows the number of GPUs in the cluster over time. In this first highlighted window, the job at the top, training Resident 50 on the ImageNet dataset, is running with 8 A100 GPUs at the start and gets scaled down to 4 A100s as new jobs arrive into the cluster. Eventually, as these A100s get allocated, presumably towards CFAR10 jobs like the one in the second row, the first job is moved off A100s and onto the RTX GPUs. In this second window, CR scales up a deep speech 2 job while exploring all 3 GPU types using its bootstrap throughput model approach. It eventually settles on RTX and Quadro GPUs, leaving the A100s free for other jobs. CR policy is also quick to compute. In this graph, we plot the median time to compute allocations as we scale both cluster and job load up proportionally. We see that CR's ILP can be optimized before a scheduling round ends, even for 2000 GPU clusters. CR can also work with other forms of parallelism and can support other forms of workloads too. If that piqued your interest, please check out a paper for more discussion on the CR objective. So, to conclude, job adaptivity is hard to optimize in heterogeneous clusters because of the large space of possible allocations. CR structures the set of possible allocations by introducing the notion of configurations. It then formulates the scheduling objective as an integer linear program that is quickly optimized for sizable clusters. And finally, CR matches jobs to GPU types efficiently using bootstrap throughput models with low profiling overhead. Using these techniques, CR reduces average job completion times by 30 to 93% and uses 12 to 55% fewer GPU hours to do so. CR is open source, and code to reproduce our experiments is available at this GitHub repository. Thank you, and I'm happy to take any questions.
Go ahead.
Hey.
Maybe let's make sure can you hear us, Suhas?
Yes, I can hear you guys.
Okay, perfect.
Okay, cool. Thanks for the talk, great work. I think this is super interesting. You mentioned that you're using the gradient statistics to periodically update, the model and see whether your policy is good. I'm wondering how tied to the gradient statistic are you compared to other parameters, maybe like the goodput progress? And the reason why I'm asking is because it seems that you could potentially extend your technique to other hardware than just heterogeneous GPUs. So for example, if you had some ensemble models that will be not only DNNs, and you have a truly heterogeneous cluster with FPGAs, other accelerators, did you think you could extend to this kind of setup? If not, why?
Good question. I think CR can be extended to the kind of setups that you're talking about. We use goodput as an indicator for progress, and specifically for deep learning models, we've observed goodput to be a good indicator of progress, job progress. And you can replace the goodput estimation with a different estimation, which, as long as you can sort of give an estimate for the performance or utility of a certain set of resources to a particular job, right? The CR can just work at this level of abstraction and do the resource optimization. So it should be fairly straightforward to support different types of goodput estimators or different types of progress estimators by using not just gradient statistics, but maybe using some other statistics from the training as well. And adding new ASICs or different types of accelerators with different topologies would amount to adding new configurations to the same problem. So that would just extend the set of allocation choices for every job in the cluster.
Thank you.
Hello, very interesting talk. This is Yang Wang from the Ohio State University and Meta. I have a question. How would additional requirements like a priority or deadlines affect the design of your system?
Good question. So with regards to weights, the CR scheduler already supports
We can implement priority using weights for every particular job type, or you can categorize jobs as particular classes, and you can have a particular type of weight for each class, and ultimately SIA supports a job level weight, which can be used to control the priority of allocations for particular jobs over the others. When it comes to deadlines, SIA does not use an estimate for the remaining amount of remaining work left in the job. So what that means is that we cannot predict the remaining time left, and so estimating the deadline is hard. But it may also just be possible to, instead of using a goodput estimator, you could replace this estimator with an estimate for the remaining time, or whether you'll be able to complete a job by a particular deadline if a job runs in a particular configuration, and you can set that to be a binary choice, which would ensure that SIA would only allocate those configurations to jobs that would make them meet their deadlines. So that is one way of incorporating deadlines into SIA without really making too many changes, and this would be optimizing potentially the number of missed deadlines. So you'll be doing a minimize missed deadlines policy. But you'll be following mostly the same process, but using a JCT estimator instead of a goodput estimator.
Okay, thank you.
Hi, Marcel from Imperial College London. Thank you for your talk. I have a twofold question. So first of all, how do you decide how to distribute the training in terms of which computation go to which GPU when you do the profiling? And then the second one, when you do the profiling, do you take the state that you already, the progress in the training that you made while you were profiling, are you taking that along, or are you discarding it every time you change the resources?
Good question. So let me try answering the first one. So the first question asked whether how do we decide where to place these, jobs in the parallelism when we use a particular type of parallelism. So we use data parallelism. And in the initial profiling, every job runs once. It's starting from zero progress here. Before it even actually starts running, we will go profile it once on one GPU of every type, or the minimum possible GPUs that the job requires. And this will give us an initial estimate of the throughputs on the minimum resources. And sorry, I think. Sorry, I think I lost track of the second question. Could you please repeat that?
Yeah. So are you carrying on the progress that you made while you do profiling, or do you start from zero every time you profile different?
Yes. So there's two types of profiling that happen. In the initial profiling, because the profiling is happening at zero progress across one GPU of each type, there is nothing to carry. So we can run that in parallel, and we don't really carry any progress over because it's probably just 15-20 seconds of profiling per GPU type. Then subsequently, every additional profiling that happens is an online profiling, in that we are not using compute only for the sake of profiling, but rather we are making job progress, and we just measure the runtime of particular mini batches while the progress is happening. So this is the combination of both offline and online profiling, where in the first case we do not carry over any progress, but in the second case we carry over progress and we just do online profiling for a couple of mini batches.
Thanks.
Okay, let's thank the speaker.